Hello, thank you. Thank you very much. Welcome. Welcome to Perimeter Institute's public lecture series presented by Sun Life Financial. My name is Greg Dick. I'm the Director of Educational Outreach here at Perimeter, and it is my sincere pleasure to welcome everyone here this evening. And we are also live webcasting tonight's event, courtesy of some very amazing technology from a local Kitchener company called Degero. And as such, we have this live web feed, which we are sharing with fellow science communicating colleagues around the globe. So I would also like to welcome our online audience from not only the Perimeter's website, but also from the National Science Foundation, the American Physical Society, Physics is Awesome Facebook page, the National Society for Black Physicists, Fermilab, Physics Central, and Cosmos. It's a joy to share this lecture with everyone. Welcome. Yeah. And I would also like to make a special welcome to Andrea Bellemare from CBC's Morning Edition. Right here, wave. Welcome. Welcome to Perimeter's public lecture series. This is fantastic. As you know, Perimeter is supported by a very successful and unique public-private partnership. One of our key partners is Sun Life Financial. And I would like to take this opportunity to recognize and for us to thank Sun Life for their continued support of science communication and our public lecture series. Thank you, Sun Life. And now, if you'll indulge me for just a few more moments, as this is the last lecture of the season, I'd like to take this opportunity to thank the team that makes these lectures possible. So first, the Perimeter staff from across departments. They are incredibly professional, wonderful people to work with. Oh, and you know what? The list is long, so let's save the applause to the end. They're incredible. They bring their very best every day. It's a pleasure to work with them. Conrad Entertainment, Peter Conrad and his crew who film and help produce this event. Tremendous to work with. The WCI staff and students. There's Jennifer Shortreed, the principal. Michael Burns, physics teacher, and his volunteer students. Jane Pentecker and her AV students that help produce the event. And lastly, but certainly not least, our Perimeter volunteers who year after year, month after month, they're here to support Perimeter's activities. They include Barbara Crossman, Sue Sittler, Sheila Santi, Marilyn Birch, Ellie Lazaridis, Scott Jones, Merv Shepard, and Dave Sittler. Please join me in thanking the entire team. The lecture will last approximately 1 hour, and it will be followed by a question and answer session. If you want to follow along online and join the online discussions, please use hashtag #PILive. And as always, I'll try to take 1 or 2 questions from the Twitter feed. And now, it has been a remarkable year. We've had the opportunity to explore topics from black holes to speleology. That's that caving one I couldn't pronounce the first time. Fusion energy, modern mathematics, the future of physics, and dark matter. And tonight, we are extremely privileged to have with us Dr. James Gates. Dr. Gates has been a distinguished visiting research chair at Perimeter since 2011. He is currently a University System Regents Professor at the University of Maryland, the John S. Toll Professor of Physics at the University of Maryland, and the Director of the Strings and Particle Theory Center. He serves on President Barack Obama's Council of Advisors on Science and Technology and on the Maryland State Board of Education. He is extremely well known for his work on supersymmetry, supergravity, and string theory. Dr. Gates has been honored numerous times over his career and most recently was awarded the Mendel Medal by Villanova University in recognition of his influential work on supersymmetry, supergravity, and string theory, as well as for his advocacy for science and science education in the United States and beyond. President Obama awarded Professor Gates the Medal of Science, the highest award given to U.S. scientists, and that was done at the White House ceremony in 2013. And he is one of the nicest gentlemen you will ever meet. Please welcome Dr. James Gates. A pleasure.
Thank you. Thank you very much. This is, as mentioned in the introduction, is not my first time in Waterloo. I try to get back here as frequently as I can. And in fact, I was here in March. I've told people that one of the great things about the Perimeter Institute, it's a place that I can go to actually do my physics, and people will leave me alone here. This condition is met almost nowhere else that I happen to go to work. Unfortunately, at this stage of my life, in my 63rd year of life, I find I have 4 careers that are simultaneously running. I don't know how I got here, but it sure keeps me on the run all the time. Physics, however, is the career that's closest to my heart. Although, I have to tell you, I've been teaching for 42 consecutive years, university mathematics or science. Been doing research of the type that you're going to hear about tonight since 1976. I've been in the media doing things like Cosmos, not Cosmos, but the Elegant Universe and science documentaries since the mid-90s. And then the policy work that I do with the Maryland State Board of Education and advising the current presidential administration through PCAST, about 5 years. And so that's 4 careers. I don't know how any of them got started, except the first one. And the first one's not teaching, it's science. Part of my story begins in St. John's, Newfoundland in 1954. Because you see, that's where I lived. There were US military bases there at the time. People forget the US military had bases here in Canada. And my father was stationed there. And one day I saw a science fiction movie, which was brilliantly, this whole story is told at the Perimeter website, so I won't tell the rest of it, but you can go here. But for me, my interest in science started here in Canada in St. John's. People are shocked to hear that. So tonight, we're going to follow an arc of a story that is part of my story in science. And you know, people often think that science and mathematics are somehow very different and divorced from the rest of the human experience. And what I like to point out is that scientists are people too. And we behave like the rest of us. We have our own quirks and what have you. And the thing that we're doing, science, is a very human activity. It's done by people. We make mistakes. We make errors. We sometimes come to loggerheads over trivial points. But at the end of the day, we're trying to produce something of great value to our species. In fact, you can hear me online saying that one of the reasons why science is so important is because our species, over not hundreds, but possibly thousands or tens of thousands or hundreds of thousands of years, will be challenged by changes in our environment. And science and the technology that comes from science will be the only tool that we have to defend ourselves. And that's the fundamental reason why we ought to be doing science. A sort of more jocular way I explain this is, look outside. I bet you don't see any dinosaurs. That's because there were no dinosaur scientists. So I'm going to tell a story. It's a story about science, but it also shows how science connects up to the human experience in sometimes very unexpected ways. So let's get started. Assuming that our technology will cooperate with us, I'll start with my bucket list. A few years ago, a movie came out called The Bucket List. And although I am sometimes mistaken for one of the stars, and you may think that's a joke, but it happens far too often in my life. I did not star in that movie. However, after seeing that movie, I thought, gee, you know, I have a bucket list. It's not about things that I want to do, it's about things in science I want to see. And so the first item on my bucket list is the Higgs boson. And on July the 4th of 2013, it was announced that the Higgs boson had been found at Geneva, Switzerland, at the LHC. And so I turned that to red. It happened in my lifetime. Gravity waves. Well, that one, maybe it should be either pink or something. We're not quite sure. In March of this year, there was an announcement by an experiment called BICEP-2, where it was observed that something called the B mode of gravity had been observed in the cosmic microwave background. Gee, what does that mean? Well, the B mode of gravity turns out to be that there's an aspect of all waves that looks like a circular spoon. And so if gravity waves are out there, you would expect them to stir up the matter near the time of the Big Bang, and it would leave an imprint on that matter, just like you stirring a cup of your coffee in the morning. That's the B mode of gravity. And it may or may not have been seen. We're not completely sure because in science, we're not perfect, and so there might have been dust on the detection equipment. So we're not sure. Superpartners, we're going to hear about that tonight. That's really what I've actually spent my career, my entire career thinking about. And then finally this thing called superstring M theory. And like I said, this is my bucket list. This last item, I don't think I'm going to get a chance to see before I shuffle off this mortal coil. But it would be great if I did. So theoretical physics works sort of in the following way. Here's a cartoon that I had created some time ago. And at this point here, you're supposed to imagine there's an electron. Let's do this one more time, so we can't get the tech there. When you move an electron, there's a form of invisible hair that moves along with it. The person who discovered this was a Scottish physicist by the name of James Clerk Maxwell. He wrote the equations that you see up here. And at this point, let me apologize. I know that for people who aren't scientists, mathematics is not always regarded as the most lovely experience. But we will have very little mathematics, but please don't bring out the holy water and start grabbing your crucifixes. It's not going to be that bad. So Maxwell wrote the 4 equations that you see up here, and his equations told a story that no one had ever figured out. It said that if you take batteries, magnets, and wires, and you do something to them, you could create a piece of electricity that went flying outside the wires. That's in our little movie here, that's the wiggling hair that you see going out. And no one had ever known that before he wrote the equations. A physicist named Heinrich Hertz said, if these invisible pieces of electricity are flying around, I should measure them. And he did in 1888. Now, most people have never heard of Heinrich Hertz either, but you've heard the expression megahertz because it tells you how fast your computer works. Well, the Hertz there is this man's last name. And then the next person in the story is sort of Marconi. He said, aha, you can measure these invisible pieces of electricity flying around? Let's use them to send signals back and forth. That's the birth of radio. And there's a direct line from the birth of radio to all of your marvelous Wi-Fi technology that you love so very much with all of those apps. And so in some sense, it all got started with these equations in the 1860s. That's the thing that is such a mind-blowing idea that it was over 150 years ago that the start of the revolution that you now partake in actually began. Dmitri Mendeleev was the first person to write down the periodic table of elements. This is what I like to call the Mona Lisa of science, because everybody's seen it. Well, maybe not this version. We'll come to the one you've seen. But this is the original version of the table as Mendeleev presented it. You will notice that it has some holes in it. And so, you know, we humans, we have this innate sense of symmetry or balance. And so when we see something like this, we say, you know, that's not as pretty as it could be. Now, you know, that's not doing science, but that's really deeply, innately grained in the human psyche, symmetry. And I, in fact, I don't know this is the case, but I have a very great suspicion that one of the reasons we have such a great appreciation for symmetry is you can imagine a hunter-gatherer family on a plane looking at the far horizon, and they suddenly see that there's a bump on the horizon. That breaks the symmetry, right? It was nice and smooth before the bump was there. And you might say, well, gee, why would they care? Well, the next question is that coming to eat me? You see, that's an existential question. The symmetry is no longer there. What does that mean about me? So I suspect that very deeply ingrained in the human experience is the expression of looking for symmetry. We know, for example, that part of what we consider beauty is tied up in symmetry. So this is not a very pretty face. This is like Mona Lisa with a few teeth missing. So you need a genius to come along and say, oh boy, should look like that. So this is a modern table of elements that you'll find in most classrooms today. All the holes are missing, are gone, they're completely filled in. And in fact, Mendeleev used those holes initially to predict the new elements that fill those holes in this table. Plus the table grew with even more elements. But you can see symmetry has been restored. This is the standard model. This is what my generation has been struggling for the last 50 or so years to understand what's in the universe when you go to the very tiny scales. We know about things like the electron. That's, in fact, the most basic unit of charge. But nature, in fact, is prolific. In addition to the electron, she copies herself by producing an object 200 times as heavy as the electron, but in all other ways than the electron. And yet she produces another copy 1,700 times as heavy, but in all other ways this thing is an electron. The first copy is called a mu particle. The second copy is called a tau particle. These things have been discovered within physics in the last 30 or 40 years. There are also things that are very closely related to the electron that have no electrical charge. They're called neutrinos. In addition, if you go inside of particles like protons and neutrons, there are tiny little pieces inside. We call those quarks. They're up-down charge range, top and bottom quarks. And each one of these quarks is triplified. That is, there's 3 different ones of them. You're not just this sea of electrons. I like to tell audiences, you're far more beautiful to look at than that. So why aren't you just this sea of particles? And the answer, of course, is that there are forces that keep these particles in fixed shapes. And these fixed shapes are the parts from which you're built. So these forces, there are 4 in nature: the strong, weak, electromagnetic, and gravitational forces. Each force has a particle that carries, at least one particle, that carries it from location to location. So the fact that you're looking at me is due to photons being boiled off of these light sources, bouncing off my forehead, being perceived in your eyes. But that particle of light that is responsible for you seeing me is also the particle that tells 2 electrons to be repelled from each other. It basically carries a message from one to the other. There's another like charge here, move away. All the forces at the fundamental level seem to act in this way. I'm a science fiction fan. And if you're a science fiction fan, maybe you've heard about Star Trek. And in Star Trek, they're always talking about gravitons. Well, gravitons are the particles that communicate between you and the Earth that you ought to be attracted to each other. So all the fundamental forces have these carriers. Now, this is the standard model. This has been underway for, since about the 1930s, we've been building this thing. And it's kind of a version of the Mendeleev table of elements, except instead of elements here, we're showing the parts that make up the elements. The Higgs particle, and let me do this again for you. The Higgs particle, 2013, we found out there was another missing piece of the table that we didn't know about. Although people like me and my community had been using mathematics to make a prediction that if you looked hard enough, you would find this thing. And after about 40 years struggle, building some of the most sophisticated devices in the history of the planet, we finally found the Higgs boson in Geneva in 2013. So that's the standard model. That's what this is the parts list for how to get to you. However, if you take these parts lists, you can parse them in a different way. You can ask, of those things that you saw, what number of them constitute matter? Matter is the stuff that you're made of. Well, we know the electron, protons, neutrons, and all of those objects are down here. Now, it turns out that tiny particles act like little spinning basketballs. And so you could ask, well, how fast do they spin? Well, it's a very funny property. Electrons have a spin. We physicists use a number called h bar to talk about how fast that is. And it turns out that every electron spins at the same rate. Every quark spins at that same rate. They're all what we call 1/2 h bar particles. So we're talking about how fast they spin. And they can either spin clockwise or counterclockwise. Now, you can ask, well, if the electrons are all spinning, what about particles of light? Do they spin too? The answer turns out to be yes. But they don't spin at the same rate as the electron. They spin at twice the rate. And so the photon, which is indicated here as yellow, spins at twice the rate of the electron. There are particles called gluons that keep the quarks buried in protons. They all spin at twice the rate of the electron. There's something called the Z particle. It spins at twice the rate of the electron. There's the W, there are 2 Ws. They both spin at twice the rate of the electron. And then finally, the Higgs particle that we just discovered, turns out it doesn't spin at all. And so you can say, that's interesting. You look at this table, and then I go back and point you to this table, and then I ask you, is that pretty? For the same reasons that the initial Mendeleev table is slightly unsettling, just purely emotionally, it has nothing to do with whether you know science, just kind of your emotional reaction to it, the universe would look much more beautiful if it looked like that. And believe it or not, this is the basic idea of supersymmetry. Supersymmetry says that when you look at all of the parts that make up matter, they should have this kind of balance so that the number of energy particles that spin at the rate of the electron, that's what's up here, should be balanced out by the number of energy particles that spin at twice the rate of the electron. That's what we see in this quadrant. That the electron in its family should have which all spin at the same rate, should be balanced by a set of objects that don't spin at all. This is the basic idea of supersymmetry. And I was a graduate student in 1976 at MIT. I was the first person at the institution to realize that the equations which had been presented slightly before I got to graduate school made this prediction that there would be more forms of matter and energy than we had ever thought about before. And I wound up writing the first PhD thesis at MIT at the time. Now, it was an interesting experience because I was very excited. More forms of matter and energy. You know, it's like a kid with a new toy. I got more toys, Dad. I got more toys, right? I could not find a single faculty member who would help me learn about this new subject. And so I wound up actually having to teach it to myself, and then I defended my thesis. And I have to tell you that for those of you who are thinking about going to graduate school, maybe you want to do a little bit like what I did. So I wrote this thesis on this subject that no one at the institution knew anything about. And so when it came time to defend it, I knew more about what was in the thesis than anybody in the room. And therefore, defending it was a piece of cake. In fact, one of the people who was on my thesis defense committee is currently the Secretary of Energy of the United States. His name is Ernie Moniz. And a few years ago, I encountered Ernie after not seeing him for maybe 20 or so years, and I asked him, Ernie, do you remember what you said about my thesis defense? And he said, sure. It was the best thesis defense I had ever seen. And I was like, wow, then I didn't imagine it. And then the funny thing that happened was when he said that, and even at the time I thought, boy, you don't know about the Kobayashi Maru. Now, for those of you who are Star Trek fans, and for those of you who are not, the Kobayashi Maru is a computer test given to all graduates of Starfleet Academy that you have to pass in order to graduate. Now, the only problem with this virtual reality test is it's programmed so that no matter what choice you make, your starship will be destroyed. In the entire history of Starfleet Academy, only one cadet successfully makes it past this test. His name is James Tiberius Kirk. And the way that he did it was the night before the exam, he rewrote some code. That's what my thesis defense was about. I had rewritten the code about how to defend the thesis. So I told you about this property called spin. It's very important. If you look at many chemistry textbooks, you'll see figures like this. They're called orbitals. What they show you is how the electrons distribute themselves around an atom. And these orbitals and their form is very important because the rules of chemistry actually come from these shapes. But these shapes come from the fact that the electron has spin. If you could magically turn the spin off of electrons, the following would happen. All the electrons would fall to the lowest energy level of the atom. There would be no shape for atoms. There would be no chemistry as we know it. If you don't have chemistry, you can't get to biology. And if you can't get to biology, you can't get to us. So you see, the fact that electrons spin is a critical feature of our existence. If electrons didn't spin, we couldn't be here. So we're going to take a journey down in size. Excuse me. Each of the marks in this represents a power of 10. What's a power of 10? Well, let's go through it really quickly. Start with a ruler, yardstick, meter stick, break into 10 equal pieces, throw away 9, keep 1. You go from something this big to about something that big. Take that remaining object, break into 10 equal pieces, throw away 9. You get something about as broad as my fingernail. How many times do you have to do that process to get the size of the atom? Now, I'm a professor, so this is your pop quiz for the evening. Now, I ask this question to lots of audiences, and almost nobody knows the answer to this question. Even though everybody's heard of atoms, nobody knows where atoms are, how big they are. So in my story, the answer turns out to be you do that process 10 times. And you go from how big we are to how big an atom is. It's only 10 times. It's not very far away. People often like to say million, billions. Some people like billions and billions. It's only 10 times, right? So if we go down in size, and this is a little movie showing that, if my technology will continue, it did not. Technology failure. But this movie was designed to show that as you go down in different sizes, you encounter things smaller and smaller. So first, blood cells, about 10 to the minus 5. 10 to the minus 9, you get to strands of DNA. 10 to the 10 is the size of the atom. 10 to the 15, minus 15, this nucleus of the atom. And at 10 to the minus 18, we don't know what goes on after that because we have no technology that can measure scales smaller than that. So if we humans are going to try to figure out what's smaller in the universe, we can't use our technology. So what's left? It turns out what's left is our imagination. But not our imagination that we use to write science fiction and mystery stories, but our imagination harnessed to this kind of stuff. You see, mathematics is essentially an element of the human imagination. Just like music, poetry, literature, all come from human creativity and use of the imagination, mathematics is the same thing. One of the questions I like to ask audiences is, next week, will there be more music than there is right now? Yes, because you know that next week there will be someone somewhere writing more music, right? Simple question. Next question. Next week, will there be more mathematics than there is right now? People often say, how can that possibly be? Well, the answer is yes. There will be more mathematics next week than there exists right now. And the reason is for the same reason there will be more music next week. People make mathematics. We create mathematics. Just like we create music and song and lyrical poetry, we create mathematics. And one of the odd things there are many odd things about the language of mathematics. One of them is that it's the most telepathic language that we have. And by that we mean you can know more precisely what someone is thinking if you use mathematics than any set of words. What does that mean? Well, suppose I say red. Okay, so you could all have a picture of red in your mind. Do I mean fire engine red? Or do I mean a pale red that's almost a pink? Or do I mean a orangish red? What kind of red? What does red mean? But if I say the number 1, you know exactly what I'm talking about. So mathematics comes as close to telepathy as any human language we have. The other thing about mathematics is we are apparently the only species on the planet that makes this stuff. So people like me use mathematics. But it's not just about balancing equations. We use mathematics as a third eye, as a way to see the universe. The first person to know the size of an atom was a guy named Albert Einstein. He did it in 1905 using mathematics. So people like me use equations like this to ask what's smaller than our technology can currently see. And since about the middle 1970s, we've been storing equations like this. So this is an equation that kind of says, well, the thing in the middle here is kind of half an electron. And remember that kind of symmetry that I showed you where I wanted the universe to be perfectly symmetrical in terms of spin and matter and energy? It says that equations like this should describe such a universe. So people like me have been studying these things. You know, you look at them and you say, oh boy, it's that math stuff again. It's even worse than that because these D's are derivatives. Oh my goodness, calculus. You know, you remember your calculus class. Come on, don't act like you've never heard of calculus. You know, not necessarily a fun occasion, but you know, they're tools, so we continue to use them. Why do we use mathematics? It turns out it's the only human language we have encountered that allows us to accurately describe what goes on in nature. There is no other language we know that works as well. That's why it's done with mathematics. I often encounter people say, well, can't you do it without math? Well, yeah, I can if I'm willing to lie to you a little bit. But if you want to know the most accurate truth, I have to do it with mathematics. So as I give a talk like this, I'm using similes and metaphors to describe actual hard mathematical facts. But I also said that it's a human endeavor. So just like we can connect poetry to our emotions, we can connect mathematics to things that you know about. And that's, in fact, the way that I give a talk like this. Wow, that doesn't look like mathematics, right? It looks just, it's a picture. Well, it turns out that in 2005, I was in Georgia, the one that is north of Tehran, a couple of 100 miles. And I saw a paper on the internet, and I sent a message to the author saying, gee, some of your equations remind me of some things that I've been playing with. And I got back a message from one of the authors, a gentleman named Michael Fox. He said, oh, that's interesting. I've been thinking about this thing. Let's talk about this. So we started an internet conversation without meeting each other at the time. And at the end of the month, we had sent questions back and forth to the degree where we had made this interesting construct where we could take the equations that I showed you in my previous slides and turn them into pictures. But not just any old suggestive picture. Every mathematical fact in the equations occurs in these pictures. Now, this was mind-blowing. By the time that we finished this, I was in West Africa, in the country of Mali. And Michael was in the Slovak Republic at the time. And so we found this picture-making way to extract mathematics, and we needed a name for it. Now, physicists, especially theoretical physicists, we're a little bit wacky. And so when we find something that's really neat, we don't give it a name that shows a lot of respect. We give it a silly name, like quark, for example. So Michael, who had traveled in West Africa a decade before I had ever been to the continent, knew about this African word called adinkras. And he suggested that we should name our pictures after these things, adinkras. Now, they don't have anything to do with traditional African adinkras. We simply stole the word. So it turns out that instead of showing you equations, I know how to tell you stories of physics using pictures instead. Probably feels a little bit better than showing you a whole bunch of equations. Now, each of the dots in these pictures turn out to be what's called a function in mathematics. So maybe you remember doing your math and hearing about functions. And there are two kinds of functions here. The white ones correspond to functions that spin like the photon or the Higgs particle, and the black ones correspond to particles that spin like the electron. So the whole spin story is actually in these pictures. There are pluses and minus signs, there are calculus. All of that stuff turns out to be in these pictures, and that's what amazed Michael and I. So here's an example of how you turn the pictures into equations. This is a simplified example. I won't spend a lot of time here, but we have a dictionary, basically, that tells us how to take a picture and turn it to a set of equations, or vice versa. Now, I have to tell you that these pictures played a very important role in the story I'm reciting tonight, because a few months before I talked to Michael, I gave a talk in Luminy near Marseille in France. It was one of the few times I spoke at a conference of mathematicians. And what I showed them were all the equations that I had been studying with my students and what have you. And I gave this talk before some of the most brilliant mathematicians in the world. And I got to the end of my talk, and there was complete silence. And I was like, why did I just do this to myself? I'm sure that their reaction was, this guy is either crazy or doesn't know anything about mathematics or some such thing, because there was just no reaction. With these pictures, something rather remarkable happens. Remember I told you all the mathematics is in the pictures? Well, the mathematics we physicists like to use. It turns out mathematicians actually think about mathematics differently from physicists. So when I found these pictures, together with Michael, I could hold them under my mathematical friends' noses and say, what is this? What do you see there? And because the information is really in the picture, they could begin to tell me a story about what they saw there. Very different from the way that I initially thought about the story, I and my colleagues. So I formed this interdisciplinary group. 3 mathematicians, Greg Landweber, Charles Duran, and Kevin Iga. 3 physicists, myself, Michael Fox, and Tristan Hughes. And we began to cross-disciplinary dialogue about these objects. So, as I was saying, when we developed these pictures, we were then able to talk to our mathematical colleagues, and they would tell us different things that were not obvious to those physicists in our group when we first started the presentations. And so, one of the things that came from this effort is a new way to understand calculus, and it looks like the technology is going to come back. So let me talk about it while we're waiting. As you raise and lower these little beads, it turns out you're doing calculus. I would love to be a calculus teacher where all I had to do is walk in the classroom, give my students some beads and thread, and say, move those around. And if you move it the right way, I'll give you an A in calculus. So let's see if all this effort has paid off. So here's one of these little figures. That was an integral, folks. You just graduated from a calculus class. So we learned that you could do algebra and calculus on these figures, and the figures actually knew about the stuff. So we have these dictionaries. We now have ways to playfully, graphically do mathematics, and then the fun really begins. Now, for those of you who might be interested in playing these games, it turns out that there's an app online that you can download for free from this URL. Anyone can get this. My colleague, Greg Landweber, who's one of our mathematicians, actually wrote some code, so you can start playing with these things if you find it so fascinating. Here's one of these objects, as I said, that we've learned to play with, and this is, in fact, massive sets of equations. Here's more of them. These are much simpler, but Einstein once said, after a certain high degree of technical skill is achieved, science and art coalesce in aesthetics, plasticity, and form. And a little bit of that started happening in this story because, you see, here's some very simple versions of these graphical ways of playing with mathematics. There's a little bit more complicated set of versions. Here's another one, another one. Now it's starting to get a little bit interesting. Even more so. And these are all equations that you're looking at. Now, it's hard to believe that these are equations. You know, you often hear mathematicians talk about the beauty of the subject. And for those of us who are not mathematicians, you kind of look at them and say, those people are crazy. But when you see the equations rendered as some of these pictures, you begin to get a sense that maybe there is a kind of beauty there, that they're in their imaginations, they're able to access these things that I can now show you in terms of these computer graphics. Now, these are massive sets of these equations in order to get these illustrations. And my wife, who was sitting in the audience, has often said that if we could find someone who weaves, she would love to have these as wall hangings. So if any of you are weavers in the audience, please talk to me afterwards. It turns out that some crazy stuff about donuts started showing up in this. There's a piece of mathematics called Riemann surfaces, and one of my mathematical colleagues quite recently has shown that these funny pictures that Michael and I started, in which the group actually began to develop, has an even more powerful connection to mathematics of precisely the nature that occurs in string theory. Riemann surfaces, it turns out, is a core foundational concept of string theory, and we find just by playing with these pictures, we get driven to the same mathematical concept. So here's one of these pictures, and now I'm going to do some matrix algebra for you. As I keep the same horizontal height and change the balls, I'm doing what's in mathematics called matrix algebra. I'm doing matrix multiplication. Again, if you teach linear algebra to your students, wouldn't it be great just to say, do that, you got an A. They'd love you more. Here we're doing a derivative. So when we change vertical heights, we're doing calculus. I'm still doing 4 integrals here. I'm going to do 3 more. There they go. And you'll notice there are 2 identical subcells now. You could not see those things from the initial figure, but they were always there. Now, since I've discovered that they're there, I'm going to try to glue the 2 of them together. Since they're identical, I'm going to say, well, suppose one is in fact a mirror of the other. Now, in order to do that, I have to do some mathematical transformations, which in terms of graphs means twisting, turning, but never breaking the links. And then finally, I can jam the 2 together with a perfect match, open them back up, and the equations that this represents were the ones that were half an electron that we met earlier in our talk. Now, the object from which we began was this. This object contained in it Maxwell's equations. And the fact that I can show you these transformations means that Maxwell's equations, which were discovered in the 1860s, are somehow connected with the equations that describe half an electron, which were discovered by Dirac in 1927. These two things are connected. But if you're going to believe that something like string theory or unified field theory exists, you want this mathematics all connected together. And in terms of these pictures, we can, if you sat down with me for, I don't know, a couple of days, I could explain the precise connections between these things. Yes, the possibilities of unified field theories do reside in this pictorial method that we've developed. Turns out there's some more weird stuff in here. So there's the object that I showed you at the beginning, and this time I've decided to name all the little balls. I'm calling them, the one at the bottom I'm calling 0, 0, 0. The one that's connected by a red link I call 1, 0, 0. The one by a green link, 0, 1, 0, 0. Blue link, 0, 0, 1. And black link, 0, 0, 0, 1. So as you change the links, you change ones to zeros. If you know something about computers, ones and zeros should make you very suspicious. Because you see, when you sit at your computer screen typing all your messages or sending your videos or listening to your music, what you're listening to are ones and zeros. You see, digital communication, the kind of communications that computers use, are nothing but ones and zeros. And then we have dictionaries, devices that change those ones and zeros either to words, to numbers, to sound, to pictures. But it's in the computer, it's just all ones and zeros. And yet, I'm showing you that there are these ones and zeros in this. And now that folding that I showed you earlier, let me describe it a slightly different way. It turns out that the folding works so that the ball at the bottom folds together with the ball at the top. The ball that's over in this corner, on the lower part of the diagram, folds together with the ball in the upper corner over in this part of the diagram. The ball that's over here on the edge folds together with the ball over here on the edge. Did any of you catch on to the game that was being played? Well, if you stop and add all the zeros in the very bottom to all the ones in the top, you get 1, 1, 1, 1. If you go from the lower left-hand corner to upper right-hand corner and add all the ones and zeros, you get 1, 1, 1, 1. In fact, if you fold around the sides and add all the ones and zeros, you get 1, 1, 1, 1. You always get 1, 1, 1, 1. Now, when we first found this result, we didn't quite know what to make of it. But one of my colleagues, Charles Duran, suggested that there's a funny connection to computers and error-correcting codes. You see, when you sit at your computer typing these ones and zeros, sending signals elsewhere, sometimes some of the ones you send is detected as a zero at the other side. Some of the zeros you send are ones at the other side. And if you had no way to correct that, then your message would be gibberish at the other end. A scientist named Hamming started thinking about this problem in the 40s, and he figured out a way to solve it. As you create your ones and zeros, your computer behind your back, without telling you, is putting in more ones and zeros. And then it sends the entire collection to the second computer. But when it adds these extra ones and zeros, it does it in a very special way. It does it in a way that's like saying 1, 1, 1, 1. That's why we call these error-correcting codes. Same thing works, by the way, when you use your credit cards. You know, you put your credit card into the machine, you type in the numbers. Sometimes you type the numbers in wrong. So how does a machine know that you typed the wrong number? It turns out the way that the numbers on your credit cards are chosen so that when the machine looks at it, it can use an error-correcting code to detect whether you mistyped it. So error-correcting codes are ubiquitous in your life, even though no one's ever told you about them. Well, so we have now found error-correcting codes in the laws of physics. This has gotten me into trouble. Now, I realized very early on that error-correct, it's kind of weird because there was a scientist named John Wheeler about 20 years before, 20, 25, maybe 30 years before I found this result, who once had this idea called it from bit. And what he suggested was that our universe was really a universe made of information, digital information, ones and zeros. And I remember when I was young thinking, that's a crazy idea. How can the universe be made of ones and zeros? How can that possibly be the complicated universe in which we live? 30 years later, in my own research, I find the equations once again are pointing to ones and zeros. And so I reached a conclusion. When I was young, I thought, Wheeler's crazy. In my own work, I found the same result, and I thought, gee, that means if you remain a theoretical physicist long enough, you too can become crazy. But Wheeler was a very interesting guy, did a lot of interesting physics. In fact, he's the person who invented the expression black hole that most of you have heard about. John Wheeler is the person who coined that expression. But Wheeler also had some famous students, including one named Richard Feynman, as another one named Kip Thorne. And the two students encountered each other. And Thorne was lamenting that Wheeler maybe was past his peak of powers, shall we say, and maybe was sort of going off the rails. And then Feynman corrected him and said, look, this guy sounds crazy, but what people of your generation don't know is that he's always sounded crazy. When I was his student, I discovered that if you take one of his crazy ideas and unwrap the layers of craziness from it, as you would one after another, as lifting the layers off an onion, at the heart of the idea, you will often find a very powerful kernel of truth. And then Feynman went on to relay to Thorne how one day, as he was talking to Wheeler, Wheeler had made the crazy statement, maybe maybe a positron is an electron moving backwards in time. And it turns out that that idea, if you express it mathematically, you wind up being Richard Feynman and winning a Nobel Prize for it. Because that's what, historically, that's what happened. So we can play with these mathematical objects. I have a student that I went out once and said, go find me all of these things. You know, that's what students are good for when you're a professor. You have some crazy idea. You say, just go find these things. And so I had a student who went out and found 1,536 of these mathematical objects. Now, we didn't know why there were 1,536 of them. He just found them. He wrote a computer code to go out and find them, by the way, because no human's going to sit there and work that all out. That shows you part of the power of computers in modern research. And when he found them, we found out that they broke into these 6 disjoint sets, which was very intriguing to us. One of my mathematician colleagues came to visit, Kevin Iga, and said, you know, that thing reminds me of a pizza. And so we often refer to this now as Kevin's Pizza. But he asked a deeper question, which is, why do those 6 things occur like that? And the answer turns out to be the doorway to how we're going to get to Arnold Schoenberg tonight. You see, let me imagine that I have an asymmetrical diamond such as you see here illustrated. If I do nothing to it, then before and after doing nothing, it looks obviously perfectly the same. On the other hand, instead of doing nothing to it, I could flip it around the vertical axis, which you can see a little arrow saying that I twisted it here. Now, if you forget the numbers on each picture, each side looks exactly the same. It looks like I didn't do anything to the diamond. That's what we physicists call a symmetry, by the way. You do something and you can't tell that something was done. If you flip around the horizontal axis, you can see the same thing. If I flip it this way and remove the numbers, you can't tell that I did anything. Another symmetry. We're going to call this the B symmetry. Doing nothing we'll call the identity, because that's what mathematicians mean when they say the identity. It means to do nothing. The A was the first flip. This is the B. And if we do them both, you do this. And again, you remove the numbers, and the 2 asymmetrical diamonds look perfectly the same. It looks like you didn't do anything. So Kevin recognized that that pie slice was, in fact, a realization of these 4 actions. This is something called the Klein-Vierergruppe. And mathematically, this is one way to write it. But, you know, I told you earlier about codes. Well, that has actually gotten me into trouble, because there are people who believe that I believe that we all live in a universe that's described by the science fiction movie The Matrix. Now, I don't believe that. But if you go to YouTube, you will find there a mashup created by some young man who never came to spoke to me, who took some results that we have found about these codes and simply asserts, therefore, we have found evidence that we all live in the science fiction movie The Matrix. Now I have to tell you, this coding thing got me into a different kind of trouble with a different group. I gave my first public talk on this subject, was at Perimeter about 4 years ago. And a few weeks after that, I was contacted by the British journal Physics World to write a story about how we found this very odd result. The story was published in July of 2010. It was the cover story of the journal. And about a few weeks after that, a blogger appeared saying, well, he didn't say, but he implies it. He's a person of deep religious faith, and his statement roughly goes as, well, if these codes are there in nature, who put them there? So this is the interpretation some of my friends say, we're all the Sims in God's PC. It could mean nothing. It could mean nothing that the codes are there. But it could mean something else that I'll return to at the end of my talk, which to me is the most exciting possibility. So back to the pizza. So I was reading about the pizza, the mathematics under the pizza, and I went to the Wikipedia to read about this mathematics. And by the way, the Wikipedia in terms of math and science is excellent. I know many times in high school, students are told not to use the Wikipedia, but I have actually used it in college-level courses, so I know how good the material is there. So you go and you look up Klein group at the Wikipedia, and you'll find a page that looks like this. And then as I was reading this page, I came across something very strange to me. The assertion was that the patterns that I had shown you related to this diamond, which were a realization of this mathematical thing called the Klein group, had also occurred as an idea in music. There's an Austrian composer named Arnold Schoenberg, who in the early part of the 1900s composed a new style of constructing music that he called the duodecaphony, a 12-note scale in some sense. And he started composing music in this scale. And it's the transitions in this scale are precisely governed by the mathematics of that Kevin's Pizza thing that I showed you. It's a weird connection between mathematics and music, the likes of which, you know, you just sit back and you say, oh my goodness, the universe is a mystery. It's magical. And the universe is. This is something Einstein told us, that at the end of the day, even if we're physicists, the universe contains a very great mystery. Here we see that playing out at perhaps a less exalted level. So I had heard some of Schoenberg's music prior to this work, but I said, well, let me go back and listen to it. So we're going to try to share with you some of this work by Schoenberg. Assuming, again, technology helps us. Now, I don't know about you, but the first time I heard a work by Schoenberg, I had a very bad reaction. I have to tell you, I continue to have bad reactions. But now I can't get away from it because it's related to something that I have done in physics. And so this, to me, is a marvelous story that sort of shows that mathematics, theoretical physics, these things that many people wish to say are so far removed from the human experience, often have very direct connections to things that we, in our other guises as humans, experience in life. The final thing I'd like to say is, I'm going to paraphrase my hero Einstein, because Einstein gave us, to me, the most lovely story about our universe ever when he wrote equations that describe the Big Bang. Now, Einstein didn't invent the Big Bang. That was done by a priest by the name of Georges Lemaitre. And so it's very interesting that the most fundamental idea in science about where things comes from a person of deep religious faith, which to me is a message about the whole argument about faith versus science. Well, there was no argument in that person, and he did both of them. So about 13.8 billion years ago, something happened. A transition occurred. And then there were enormous transformations of energy and space, and the universe began to grow. And at first, the universe was so compact, even light could not travel through it. At about 380,000 years after this event, which we currently call the Big Bang, light could freely begin to flow in the universe. And there occurred something which you can see in the night sky right now. It's called the cosmic microwave background. You can go read about science. It's up there every night. We can't see it with our eyes because it's in a form of light that is the same that your microwaves cook in. You know, you can't actually see microwave radiation. If the light bulb goes off in your microwave, you won't see any light in there, but your food will still get cooked. So there's an invisible form of light there. That's what the cosmic microwave background is about. And so the universe does all of this amazing stuff over these 13.8 billion years. And in this entire time, the universe creates exactly one copy of you. Think about how precious that means each of us is. And if that's the case, then how do we discount each other? That's a message of science. That's the power that science gives us. And so when I start connecting music to string theory, it's just but a tiny step of this enormous story about our connection to the universe. The story that Carl Sagan said, we're all made of star stuff. It's the same story. You are each a participant in this adventure of science. Thank you.
That is fabulous. Fabulous. Fabulous.
I have a few acknowledgments because the kind of presentation I gave, no one person could put this together. And I have a lot of people I have to thank, my collaborators, my students. You can see some of the names listed here. I also have to thank a company called The Teaching Company because they allow me to use graphics that I created for a product they called Superstring Theory, the DNA of Reality. It's a commercial product that you can buy, it turns out. I have a wonderful graphic artist named Ferguson that helped me put together some of the images. And because I use the Teaching Company's images, I'm kind of obliged to show you this. Thank you.
Terrific. Good stuff. All right, you can take your spot. All right, let's open the floor to questions. We'll have microphones coming on both sides. Just raise your hand, and they'll bring the microphone to you. Try to keep your question concise, because I suspect there'll be plenty, and we can work our way through. And the microphone's coming to you first. Well done.
Hello. Have you ever met Carl Sagan?
I have not met Carl Sagan. However, I do know Neil Tyson. And in fact, Neil tells me we first met around 1979 when he was an undergraduate at Harvard and I was a postdoc there. I don't actually remember that meeting, but I do remember meeting him a few years later when he was at the University of Texas in Austin. And so I've known Neil since at least 80 or 81. I knew the wonderful story about his meeting Carl Sagan long before it was told in the recent Cosmos series. And I also know Ann Druyan, who's Carl Sagan's widow. So I never had the pleasure to meet Carl, though.
Okay, I'm going to go to the Physics is Awesome Facebook page, and here's the question. Do you remember what you were doing when you heard that the Higgs boson had been confirmed experimentally?
Well, in the run-up to the announcement of the Higgs boson, there had been lots and lots of rumors going through my community that it had been found. So a lot of us had our ears up and, were paying attention. And for me, the thing that I knew there was going to be a major announcement was when I heard that Peter Higgs had traveled to CERN. Because for no other reason, Peter Higgs is, a fairly mature man, and not necessarily in the best of health, as all of us would be if we reached such an august number in life. but the fact that he traveled there sort of let me know. And so when the announcement came, it was kind of anticlimactic for a lot of us because we knew about all this stuff going on.
Very good. Let's go here to my left.
I just had a question with regards to something said in the end of your talk. You said the Big Bang occurred 380,000 years after that initial event, and I just...
No, I'm sorry, let me correct you.
Okay.
I did not say the Big Bang occurred 380,000 years after the Big Bang. What
so-
I said was that light was freely able to travel through the universe for the first time at 380,000 years after the Big Bang.
Okay, then, thank you.
That's classroom management. That's good stuff. There's a question I see at the back. Great question. Thank you.
I'm just curious how prevalent chirality is in the supersymmetry work that you do.
It turns out, well, this is a technical question, so I'm going to have to give a demonstration of chirality. It works like this. Okay, so I did that twice. We're not finished with the demo yet. I did that 4 times. I did not do them equally. Chirality has to do with the fact that when things are rotating, sometimes when you rotate them one way, it is not the mirror image of rotating them the other way. And that's why the demonstration I showed you really shows chirality. And it turns out that the equations of supersymmetry and those little 4 equations I showed you with the funny little figures, chirality is actually broken maximally in those equations. So chirality is, in fact, a fundamental feature to supersymmetry. The other thing I would tell you is that the methods that I use to do these stories are not accepted by all physicists. In fact, I have friends and colleagues who think I'm still crazy. But nonetheless, this is the mathematics I can see. And I can show you the mathematics, and that's valid.
Thank you. Right here, please.
In your recent quest to study these mathematics and their links with things in music and aspects of life, has your thinking changed? Do you see the world in these patterns versus how you might have thought of things 20, 30, 40 years ago?
Well, let me go back to 1970. Which is about 43, 42 years ago. I was an undergraduate at MIT in my second year in the spring of 1971. And I took a course in quantum mechanics. And I saw in this course the so-called Schrödinger equation. The Schrödinger equation is one of the great equations of theoretical physics. Now, I have to tell you that I first saw the Schrödinger equation when I was about 8 years old. And I remember seeing it. And I remember the following experience. There was this thing with a bunch of funny symbols. There was an equal sign and some plus signs. And I said to myself something like, oh, that's a form of arithmetic. Because the only things I recognized there were the equal signs and the plus signs. So as a sophomore at MIT, to suddenly see this thing that I had had this encounter with as an 8-year-old child, which was remarkable because it was like walking along a seashore and seeing an especially beautiful seashell and picking up and listen for a moment, wonder about what the mystery is and putting it down. That's what my first encounter with the Schrödinger equation had been. So when I was a sophomore, I found out I could understand what the equation was saying. A few weeks after I began that course, I had a kind of a waking dream. I was sitting in my room and I was looking out the window, looking at a tree that was in full bloom in the summer. And I remember having this waking dream about imagining what that equation implied for a single electron in a leaf. And so you see, I've always actually sort of had these interesting emotional reactions to the mathematics that I learned. So this is not new for me.
Let's take the last question from the Twitter feed, and maybe a bit of a loaded question, but I think you'll like it. CERN is currently being upgraded. Do you have any predictions what it will tell us about supersymmetry when it's back online?
Well, first of all, let me say that I'm very much aware that many people, let me go to my screen here to answer the question. There are many people who, because we have not seen supersymmetry, will tell you that's good enough for our universe. It's okay that it looks like that unbalanced way. Now, they don't say that in words, but that's effectively what their point of view is when they say there's no supersymmetry there. Now, I am not able to make predictions about what's going to happen when CERN goes on. I think one of the most terrible things that physicists can do is to lead the public to believe that somehow we have these super magical powers, because we don't. We're just like you. I said that very early on. So no, I don't know what the predictions are. I am hopeful that we will begin within the next decade or so to see evidence of supersymmetry. I have a personal reason for that hope. It would mean that I didn't waste my entire professional career.
Ladies and gentlemen, Professor James Gates. Oh, thank you so much. Wonderful.